pick up where we left off on 6.2. So we had talked about the law of cosines, and we talked about how it's an adjustment on the Pythagorean theorem. And it basically takes into account what happens if I take that right angle, gamma, and I make it a little bit bigger or I make it a little bit smaller. It makes an adjustment on the Pythagorean theorem by either adding a little bit to the square of the hypotenuse or subtracting a little bit from the square of the hypotenuse. And we went through and we did several problems. And can somebody tell me something cool about the law of cosines in comparison to the law of sines? Logan. There's no ambiguous case. You've either got a triangle or you don't. And if you've got one, it's going to solve it and it's going to get the right answer. The big problem with the law of sines is when you're trying to find an unknown angle, you do sine inverse, you're only going to get acute angles. So if you happen to be trying to find, without you knowing it, you're finding an obtuse angle, your calculator will not give you an obtuse angle using the law of sines. If you use the law of cosines, if you have enough information to plug it in there, it will give you an obtuse angle because the range of cosine inverse is from 0 to 180. Okay? So good thing to keep in mind there. We did this problem right here and I showed you, once we figure out where were we here? Once we figured out what this angle was right here, figuring out this angle right here could be done by subtraction, but you could also do it by just switching things around there. And just recalling what's typed into your calculator and you're all set to go. So we've got a couple more examples that I want to take a look at. This is an example that's similar to some of the things that you're going to see in 1060. It's a navigation problem, and the bearing system on this one is not that north 30 degrees east and stuff like that. It's the more typical one, and I'll show you what that looks like. And then these problems right here, these are actually on your assignment. So we're going to take a look at those, and I want to make sure you're clear on how those work. And then I'll give you a little bit of time to work maybe, and depending on how much time we have left, I would like to get started on 6.3, just so we have some of the vocabulary that we need to work with vectors. So this says, Andrea and Carlos left the same airport at the same time. Andrea flew 180 miles per hour on a course with a bearing of 80 degrees. And Carlos flew 240 miles per hour on a course with a bearing of 210 degrees. How far apart were they after 3 hours? Round your answer to the nearest tenth of a mile. So let me explain this bearing system. Does anybody have, a mom, a dad, a sibling, or somebody like that who's a pilot? Taking any pilot training? Okay. Here's how they come up with their bearings. Okay. North starts as 0 degrees. And then east is 90, south is 180 degrees, and west is 270 degrees. So if somebody says, hey, I'm flying on a bearing of 90 degrees, they are heading due east. They're heading directly east. If they say their bearing is 225, there's 90, there's 180, 225 would point us over there. Now you'll notice a big difference here, and this is the struggle between the way they actually apply these type of ideas in navigation and that sort of thing, and the way we think of this in trig. Two things. They start from north, and which way do they go? They go clockwise, okay? When we're talking about angles, we start in standard position, and we go counterclockwise. So there's a big difference between the two of these. So what you need to do is you need to draw a picture, and we're going to be drawing lots of these little crosshairs where we've got northeast, southwest. And we're going to keep track of it that way, just like if they give you the bearings in this system right here. Okay? So here's what we've got. We've got Andrea flew at 180 miles per hour with a course of bearing of 80 degrees. So from the airport, this is what happens. She takes off and her bearing is 80 degrees. So this angle right here is 80 degrees. So she flies at 180 miles per hour for 3 hours, I believe is what they have there. How far apart are they after 3 hours? So she heads off here, 180 miles per hour. Okay, Carlos flies at 240 miles per hour, and his bearing, the bearing of his course, is 210. So again, from north, this is the same airport they take off at. From north, his looks like this. This is 90, this is 180. He'd be heading off in this direction right here. So this whole angle is 210. So So I'm gonna write that on the outside just for convenience sake. That's 210 degrees, and he's traveling at 240 miles per hour. Everybody good there? So if this is, so there are a couple different ways to do this. If this is 80 and this is 210, one of the things that we need here is we need to know what is this angle between them. Now, there's a quick way to figure that out, but there's another thing that's also very valuable to be able to do. So I'm going to blow this up just a little bit. If this is 80 degrees, how big is this little sliver that's left in between north and east? That's 10 degrees. Pretty easy, right? If this is 210 degrees, how big is this little sliver that's left in between south and the bearing of the airplane? That's going to be 30, because this is 180 degrees is due south, so that's going to be 30. Okay? Well, answer this for me. What's this little sliver in between them? It's 90, because it's the difference between east and south, so that's going to be 90. So if I add those together, I end up with 130 degrees. Now, on this particular problem, is there an easier way to figure out that that angle is 130? What is it? Yeah, since they're measured from the same direction, from north is 0, if we did 80 here and 210 here, the difference between their two bearings would be the difference between 210 and 80. So if I take 210 and subtract 80, I end up with 130, okay? So I'm going to shrink this back down so I've got room to draw here. So I'm going to draw a triangle that looks like this. And this is 130 degrees. Now, what we're really after is, what is this? What is that distance there? Now, I've put 180 miles per hour here, and I've put 240 miles per hour here. Do I write 180 and 240? Nope. How long did they go? 3 hours. So I multiply this by 3, I get 540 miles. So she's 540 miles away from the airport at that point. And I multiply this by 3, and this guy's 720 miles away from the airport. Is this enough information to solve this? Yes, it is, because I have side, angle, side. I have the angle that created the side, and I have the two other sides that are used to create that triangle. So I'm going to do x squared equals, I'd do 540 squared, 720 squared. Good thing you got a calculator. 2 times 540 times 720 times the cosine of 130 degrees. And then what is how do I find the answer from that? Take the square root, okay? So I throw that into the calculator, it spits out an answer. I'd want to make sure that I'm in degree mode. Okay, how big a number are we looking for? Pretty darn big, right? Bigger than 540? Absolutely. Bigger than 720? Quite a bit bigger. This is a very large angle, okay? Very obtuse. We're expecting a very huge distance right there. So again, we can type all that into the calculator. It's not like you have to figure out what 540 squared is and then 720 squared and then subtract 2 times those. You can just type the whole thing into your calculator, as long as you do it correctly and you're in degree mode, and it'll spit out the answer. $1,144? Is that right? So 1,144 miles. 0.4? 0.47 miles. So about a half a mile. 1144 and a half a mile. Okay? So there would be the answer for that. Okay. Again, this reckoning system, this is used much more often. The textbook we're using was probably published in the early 2000s, and I'm not sure why they chose to use that particular type of reckoning system and of giving bearings compared to northeast, southwest, and that sort of thing. This is much more common. You should be familiar with both of them. So notice, if they only give you a degree, it's always measured from north and we go in a clockwise direction. Okay? And again, just to reiterate, why would it be a good idea to use the law of cosines even if it's possible to use the law of sines on a particular problem? Okay, you can keep it exact, and especially when you're finding angles, the range for cosine inverse will find any angle you need. You don't have to worry about, do I have to take this and subtract it from 180, or is this the actual answer, and stuff like that. Okay, any questions? Okay, these problems are on your assignment, so let's take a look at this. Let's take a look at number 17. And one thing we want to take note of is, so it says, complete the table by solving the parallelograms shown in the figure. So I have a parallelogram, so there are a couple things that we'll want to remember about a parallelogram. And it says the lengths of the diagonals, the entire diagonals, are given by C and D. So when they say C, it's not just this piece right here, it's the whole thing. The whole thing is C, and same for D. A is this side over here, and B is this side over here. Okay? Any questions? Okay. Let's take a look. You may or may not use these. You don't have to write these down, but I want you to just keep these in mind. Okay, when you've seen geometry, and has everybody in here seen parallelograms before? Okay, just let's remind ourselves of a couple things. Again, don't write this down because this might make it harder to use this diagram. If this side is A, how long is this side? That's A. If this is B, this is B. Okay. Parallelograms have opposite sides that are equal and parallel. So these two are exactly the same length, and they head off in exactly the same direction. They're parallel. These two are exactly the same length, and they're also parallel. That's why we call it a parallelogram. Another thing is, if we draw the diagonals bisect each other. They cut each other in half. Okay? Another thing to keep in mind is, since this line right here is parallel to this line right here, if I knew that this angle right here was alpha, is there another angle on here that I could mark as alpha? That one right there, right? Okay. Alternate interior angles are equal. And can you tell me anything about these two angles right here, like that angle right there and that angle right there? These are called consecutive angles in a parallelogram. Consecutive angles are, they're not the same. They add up to 180, okay? Remember that in a quadrilateral, a four-sided figure, we have 360 degrees for the interior angles, okay? And because this picture over here is kind of a carbon copy of this picture over here, if you just kind of rotate it a little bit, these angles would have to add up to be 180, and those angles would have to add up to be 180. And if I were to do this, how about that angle and that angle? Also supplementary. They also add up to 180 degrees. Okay? Any questions there? Okay, those are just some good reminders for working with parallelograms. We may or may not need all of that, but at some point those things are going to come in handy. I do want you to make note of this. When they say theta is 45, they're talking about this entire angle. Even though it looks like theta is only part of this triangle right here, this left triangle, it's not. It's that entire angle. And if you know that's 45, this is the Greek letter phi, okay? How big is this angle right here? What is it? 135. So that's 135, okay? Then we want to find the measure of the diagonals. So for 17, here's what I'm going to do. I'm going to draw that triangle right there. I'm going to mark phi as 135. I'm going to mark A as 5, and I'm going to mark B as 8. Can I figure out what C is? Absolutely, using the law of cosines, right? So I'm going to do it this way. I'm going to say C is equal to big square root, right? 5 squared, 8 squared, minus 2 times 5 times 8 times the cosine of 135. That'll tell me what C is. Do I use this diagram to figure out what D is? I don't, okay? So I'm going to draw this one. That's 45. That's 5. That's 8. We'll call that D. And again, this is something that's kind of cool about the law of cosines and kind of cool about using the calculator. If I set this up here, I get D equals big square root. What am I going to put here? The same exact stuff except for 45 degrees rather than 135 degrees. So if you've typed this into your calculator, all you need to do is just edit that to be 45 degrees, and that will spit out the answer. Okay? Any questions? Sure? Okay. So you've got 18. I'm going to give you a couple minutes to do 18.